is Jeremy Lim. I am a student here at the Autonomy Incubator. And my project, what I've done here is to support MiceHab. What I've done here at the Autonomy Incubator is support MiceHab in creating an autonomous control system for their project. But as a student of the incubator, I first should explain how the incubator works a little bit. The incubator utilizes the agile approach to software development, and this means a couple things. I will go into what this looks like on a day-to-day level. So each day we would start off with, say, a daily scrum, which is just a quick meeting, get together, interns. So for the interns, this would look like we'd all meet together along with our mentors and discuss what challenges we had encountered, what we would do for the next during the day, and kind of plan our actions for the day. And then this kind of leads up to a weekly sprint where we have a larger meeting with everyone in the incubator. We present on, hey, what we've done during the past week, what we were planning to do in the next 2 weeks, and then what issues we run into there. So it's kind of a larger scale of the daily scrum. And then we move on to, and then each month we have a showcase where we kind of show off, hey, this is what we've done during the past few weeks. We're doing stuff. And that helps us kind of spread the word about what we're doing. The larger version of that is the quarterly storyboard and demo, which is a larger demonstration that we work up to during each quarter. Now, I've explained a little bit about how the incubator works and runs on a day-to-day basis, but I think I should explain what exactly my project. Here's an example of what I present during a sprint meeting. So this would be kind of a quad chart, and this kind of also introduces my project a little bit. I explain my objectives. Here, in this case, it is to provide software and hardware integration for the MiceHab project, and also to demonstrate another use of the AN architecture. And I will explain in detail the AN architecture later in this presentation. My approach would be I define kind of the software requirements for this project, and then I design the software architecture I'd use for this, and I go ahead and start implementing this. At the end of this approach would be, of course, demonstrating the system functionality of the whole system. For milestones, we have, in the category of milestones, I talk about, during a sprint meeting, I would talk about, what I've done in the past few weeks. Here, I just have some general milestones laid out here. I have defined general project direction, hardware integration. And at the end, you notice we have these yellow triangles. Those are things that are incomplete or works in progress. By the end of today, they'll be completed because I will be finishing my final demonstration today. All right, so this is all fine. But what is MiceHab? MiceHab stands for Multi-Generational Independent Colony for Extraterrestrial Habitation, Autonomy, and Behavioral Health. It's kind of a mouthful, but the acronym is really descriptive. Think Mice Habitat. The idea is to launch a colony of mice into lunar orbit and study the effects of living in partial gravity and microgravity, and study the long-term effects of that on a mice population. This is important because we know very little about deep space travel and staying in space for long periods of time. So this kind of experiment would gather really useful information that would help for deep space missions that manned deep space missions that we would like to go. And just explain some of the diagrams here. This is kind of an example of what the actual habitat. Would be the actual habitat pod. This is kind of the model of the satellite that would be launched into the orbit. By the way, this wouldn't be considered completely zero gravity. It would actually be rotating to provide partial gravity, to simulate partial gravity. This is kind of a cross-section of what the capsule would look like with many, many different enclosures in this capsule. And here's kind of a draft of what the enclosure would look like. So, project requirements. So here are some of the project requirements. We have, obviously, the colony has a physical constraints. We can't launch everything up into orbit that we want to launch. It has to handle a large population of mice. The idea is that this project would there would be multiple generations of mice born and living in this kind of situation. So the system, as we design it, has to be able to handle long durations without human contact. We have specific hardware we're using for the actual 2-scale mock-up, and you've probably noticed the mock-up here. This is 2-scale, but it's kind of a cross-section. In the real model, you would have this kind of area extending all around the central platform. And for this model, we have some specific hardware constraints. We are using 3 Odroids, an Odroid XU3 and 2 Odroid C1s. These are kind of single board computers. If you're familiar with Raspberry Pis, that's what these are similar to. And you can't see it buried in there, but we have 2 Arduinos buried in the mesh in here, in the mesh of wires and electrical circuits to control the stepper motors and the actual robotic arm we're using. And there, of course, are some more general requirements. There will be some you'll require automated behavior to take care of the day-to-day day-to-day needs of the mice. We will need to obviously replenish their food supply, replenish their water supply, and also move enclosures around to allow painting. Excuse me. Allow mating so that we can control the mouse population. We'll also need more higher level. So we'll also need to handle unexpected. We'll need autonomy to handle occurrences that are not part of routine. This project is designed so that we will be in orbit for long periods of time without any human contact. So say a year at a time between 3 supply missions. Any problems that happen will have to be handled autonomously by the system. All right. So this kind of feeds into the software requirements, and I was dealing primarily with building a software system for this project. The software system has to have a couple of distinct components. We must write code that actually interfaces to the hardware. That makes sense. You have to control the hardware in order for it to do anything. We also need a command and control structure. This is going to be autonomous, and it's going to have to it'll have to do any behaviors by itself. So we're going to need some sort of architecture to say, okay, do this at this certain time, or stop doing this if something like this occurs. We need a kind of a command and control software structure. We also will need to measure the health of the hardware and software during this mission. We can't expect everything to go right. There's probably, at some point, something will break. Maybe the arm will break. Maybe the separate motors will break. Or maybe the software will have a flaw, and we'll have to deal with that in orbit. And of course, they'll have to evaluate the mission status, take data concerning the mice, their health, and how well it is doing at maintaining the mouse population. All of this software capability will be built using AON, the Autonomy Incubator's software architecture. And I will move on and explain AON right here. So AON stands for Autonomous Entity Operations Method. it's a software framework that the Autonomy Incubator has developed for use it for our different various research projects here in the incubator. It's a framework that breaks up a given task into subtasks. The idea is that we can write several different programs running simultaneously, and I'll call them nodes from here on out. These nodes we develop these nodes kind of independently, and then after we develop them, they are interfaced. They're interfaced using DDS, which allows them to communicate with little issue. DDS stands for Data Distribution Service. It's a standard that allows different processes to communicate to each other. And this kind of allows for very quick development it allows us to interface different nodes together in a very quick way. So for example, if somebody writes a node that takes image data and processes it into coordinates. Maybe you have a camera tracking an object, and you wrote software that says, okay, we can track this object and publish this data onto DDS. That means we can use that program in different projects all around because it is not specifically linked to the project. It kind of allows for modular construction of different software systems. Aon uses a publisher-subscriber model so that when you write a program, you would write it thinking, okay, what information is it going to take in? And when it publishes, let me back up a little bit. The publisher-subscriber model is basically you have several topics, kind of repositories of information. So if you have a program, say, let's go back to this camera program example. You're publishing information about an object onto this topic. That's kind of set out as a resource to any other programs on DDS that allows those programs to take data from that without worrying about specific process information. So let me move on a little bit to the actual architecture, how I designed. So first off, I'll go through the hardware interface. Here I have three nodes that are talking to each other. We have the ARM controller, hardware controller, and cage operations. The ARM controller and hardware controller, these would actually talk to the Arduinos directly. They would receive information via DDS that would say, okay, for example, the ARM controller, where should I move the ARM? This ARM controller would send that information to the Arduino controlling the ARM, and the ARM would proof it. In this setup, I have a cage operations node that takes commands from, say, a mission and control structure, breaks them down into ARM trajectories so that these controllers can use these commands more easily. Another interesting feature about this is there's a task feedback, so that when, say, for example, an ARM is finished moving, it will publish to the task feedback topic and say, okay, cage operations, I finished moving. Now we'll move on to the mission control side of software. I've currently implemented mission control to act as a queue of commands. In this case, it would be the user that would be able to type in commands and send them to mission controller. And mission controller would send these commands off to the hardware in order to actually do what you have commanded. The interesting thing about this, though, it doesn't necessarily need to come from the user. There could be any other command sources. You simply have to create a node that publishes to this topic, and then you could have different sources. And this allows you to not just link the mission to your user, as I have it set up here. You could make this more autonomous. And next is the system health component. This is set up so that you can have a system health monitoring process that takes in information from a health and update topic. And this topic will be published to by every node in the system, so that this process knows that at all points in time which nodes are functioning okay, which nodes are running, which have errors, and the system health monitor will publish this information to a system status info topic. that say the mission controller would be able to adapt to say maybe a node has crashed or something, or maybe we have a hardware issue. So the mission controller could decide what the best plan of action is after that. All right, so all this architecture stuff is good, but I think and here is kind of a flowchart of how it looks all together. As you can see, it's kind of all flows to the mission controller. All right, so all of that stuff is all fine and dandy, but I think we kind of want to see this move. So, indulge me for it. All right, well, here's my computer shell. So I will just show you a video of our mechanism in action. This would be an example. Computer shell. So, you see, this is an example of the procedure of pulling out a cage from the holding area to the center platform. This particular video is actually manually controlled, but this demonstrates the fact that the hardware it demonstrates the feasibility of doing the center platform. This is an operation that in the future will have to be very robust, and it is definitely a very common operation in this kind of design. All right, thank you to that. I might actually be able to get the hardware even here. So, yeah, I'm afraid it looks like I've lost connection here. Looks like we have no response. All right, so I'll just continue.
So why don't you talk us through what's happening on the movie? Somebody just got really, really excited. I think that was
great. This was kind of our first successful attempt of moving the from the side system onto the center platform. With this particular design, it's been a challenge. So here we are, we're attempting to push it back. Previously, we had only one motor powering this arm, and then we upgraded to 2 motors because we just didn't have the torque. This is working much better than our previous.
So what's the software doing?
Doing?
Yeah. What's the software doing? What are the nodes that are running? What information is being passed back and forth? Or would be being passed back and forth if this was fully autonomous?
So if this was fully autonomous, you would send a command from mission control, and then you would tell them you would send an abstract command from mission control. It would say, okay, pull out the cage, and in this case, it also put the cage back. You would send the mission control would receive 2 commands: pull the cage out, put the cage back, and then would send that off to the cage operations node. That would break those commands down into separate movements. It's like saying to somebody, okay, I want you to make a grilled cheese sandwich. You would tell them, make a grilled cheese sandwich. But of course, making a grilled cheese sandwich has many steps. You have to get the bread, you have to get the separate ingredients, put them in the pan. So what happens is we kind of break down the high-level commands, moving cage in and out, into small commands, lower-level commands, like, for example, specific arm movements or specific rail movements for the stepper motor that's mounted on the rail. And then it would break those commands down into a list of those commands, and then it would go through and execute the list of those commands, with the software sending the commands piecemeal to the Arduino side controlling arm. So you send a high level command, it breaks down to a lot of sub commands. So some things I learned from this project. Clean coding pays off. Every time I've sat down and created some code, thought of a better way to implement something, or made a decision to say, hey, I'm writing these lines of code over and over again. Why don't I put this into a function so I have it in one place? Every time I've done that, it's made it easier. And every time I haven't done that, it's made it harder. So that is one lesson to learn. Learn how to use Eclipse IDE, Git. Git is a very useful tool. understanding the fundamentals of DDS and Aeon, that's just a lot. It's a lot of software system learning experience for me. Yes, utilize abstraction and automation on code projects. It's very, the more I use automation on code projects, say like automatically updating files after I've changed them, it makes it so much easier to develop and it makes it much easier to get a system up and running faster and probably better, running more smoothly. Always make sure the software has a stop button. Yeah, you see here, this is our previous arm that we had here. You notice that this arm doesn't quite look like it. We burned out a servo when we were experimenting with getting the cage onto the center platform. Accidentally forced the servo, it burned out. So yeah, two things. Daily sacrifices to the engineering gods in the form of spare parts. Always have spare parts. If you think something's going to break, get spare parts. And being able to stop the software without burning the motors out is invaluable. So, possible future work. Due to the fact that I only had 10 weeks for this project, there are some things that inevitably got left out. This is one of the big things I think that would be the next step for the software architecture after getting the basic hardware functionality, is actually getting sensor interpreters into the system. Like, for example, we were toying with the idea of having a Lepton thermal camera, being able to take, say, heat data, temperature data of mouse, of the different mice enclosures, and we would add that to our architecture, so that would inform, so we could get an idea of, say, what's the mouse like right now, what's its state, and then kind of process that and send that off to, say, mission control, so we can make decisions based on, okay, if the mouse is, for example, really cold or sick or even dead, we can choose a different course of action. And that's how that would integrate into the current software system. The information would flow directly to the mission control. All right, so I'd like to thank everyone who's been I'd like to thank everyone on the MiceHab team for just making MiceHab happen. You know, I did the software, they did the hardware.
There's a demonstration tomorrow, right?
Yes.
Of MiceHab?
Oh, that's a good thing.
Demonstration.
When is the demonstration and where?
Tomorrow morning, about 10:30ish, will be ours, over in SNAP.
Thank you.
So thank you guys. This is awesome. Jim, for entertaining countless questions of me hovering over his desk. Almost every day I was there asking him questions. Helped me so much. Thank you, Danette, for just general leadership and helping me go through this presentation. And Chan, Gil, and Mikhail for imparting the secrets of Linux, C++, and DDS. Yes, helped me many times. And Kyle, a special shout out to Kyle. Where is he? Where's Kyle? He's hiding back there. He helped me with some of the, actually writing some of the software as well. So, and I'd like also to thank the entire Autonomy Incubator team as a whole. Incubator is it's a really great environment. I can't say anything more than that.
All right. Thank you, Jeremy.